Now let us discuss the bunching process and the Applegate diagram of the two-cavity Kylstron amplifier. As you observe in this diagram, we have mentioned three time intervals TA, TB and TC. TA is the time at which the slower electron is present. TB is the electron which does not get modified in its time characteristics, which means it doesn't get either accelerated or decelerated, it travels with the same speed. And TC is the electron that travels much faster because it gets accelerated. And TD is the point at which all the electrons get bunched together. So we have four time values: TA for the slower electron, TB for the electron that travels with the same speed, TC for the faster electron, and TD to be the bunching center. Now the time difference between the two electrons, like the slower electron and the same speed electron, and the same speed electron and the faster electron is pi by 2 omega. We can write TB as 2TA. If I add a time interval of pi by 2 omega, we can reach TB. Similarly, TC is TB plus pi divided by 2 omega. Now, let us consider the time. First, we will take the same speed electron because it does not get altered. So, at time t is equal to TB, we are going to write down the length of the buncher gap. So, we know the distance is equal to the time into the velocity value. So, the buncher gap distance is given by del L, and the time for the same electron is, if I subtract TB from TD, that is the time at which the same speed electron is traveling. So, TD is the total time distance and TB is this time distance. So, if we subtract the two time values, we will be getting the time that is required to reach the bunching center. So, it is TD minus TB, the velocity remains the same, so we write it as V naught. Let this be equation number 10. Previously, we had mentioned 9, so I am continuing with the number as 10. Next, we will take the next electron at time T is equal to TA. So, which means it is your slower electron. So, the buncher drift space, the length of the gap is given by TD minus TA into, it is decelerated because it is slower electron. So, velocity will be the minimum velocity. Let this be equation number 11. And for the faster electron at time T is equal to TC, this distance will be TD minus TC, and since this is a faster electron, it travels with maximum velocity, so it is V maximum. Let this be equation number 12. So with reference to the diagram, the Applegate diagram, we have written down the del L value, which is the drift space length for the electron traveling with the same speed, which is decelerated and which is accelerated. Now let me take equation number 11 and for further analysis. So from equation number 11, we can write delta L is equal to TD minus. Now what is TA? If you observe from the previous equation, from this equation, TA is TB minus of pi divided by 2 omega. So this I can write it as minus TB minus of minus becomes plus pi by 2 omega, and V minimum we already found. What is the minimum velocity? It is V naught into 1 minus beta I V1 divided by 2 V naught. Now we will multiply this V naught inside. So this becomes TD minus TB plus pi by 2 omega into V naught minus beta I V1 V naught by 2 V naught. Now we will perform multiplication for every term. So we are going to multiply TD minus TB with these two terms and pi minus 2 omega with these two terms. So therefore del L becomes TD minus TB into V naught minus TD minus TB into beta I V1 V naught divided by 2 V naught. The next term plus pi by 2 omega into V naught minus pi by 2 omega into beta I V1 V naught divided by 2 V naught. If you observe this last term, we have the term V1 by V0. And the initial assumption, what we assumed was V1 by V0 becomes 0. So this total term is going to become 0 for us because this is time independent. This does not get accelerated or decelerated. So this term is time independent. So therefore we write the term V1 by V0 to be 0 here. So what are the balance terms present for us? This will become del L is equal to, now Td minus Tb into V0. What is Td minus Tb into V0? It is del L from equation number 10. So this first term Td minus Tb into V0, I am going to replace this as del L, and once again Td minus Tb into the term V0. So this will become minus del L beta I, beta I V1 divided by 2 V0 plus pi by 2 omega into V0. Now this del L can get cancelled. We will bring this term to the left hand side. So this becomes del L beta I V1 by 2 V0 is equal to pi by 2 omega into V0. From this we can find out the length of the drift space del L to be. So del L is equal to, this will become pi, we can cancel out 2 and 2 on the other sides here. So it is pi V0 into velocity divided by, we have the omega term here, the beta I comes down and the V1 comes down. So this is the length of the drift space. Let this be equation number 13. So using the velocity modulation process, we have actually found out what will be the velocities before the gap, after the gap, and the length of the drift space. Now let us start with the current modulation process. Right. Now we already wrote that the DC transit angle, we mentioned the gap transit angle, but now we have to write the DC transit angle because it has already passed the gap. So we know that theta is equal to omega into 2. So now it is omega L by V0. Previously it was omega D by V0 because it was with respect to the buncher gap. But now it is with respect to the drift space. So we write it as omega L by V0. The bunching parameter of the Kylstron is defined. So the bunching parameter of the Kylstron is defined as x is equal to beta I V1 divided by 2 V0 into theta naught. This is one of the defined equations. This is by definition we write the bunching parameter of the Kylstron. Next, the fundamental component of current we have to write. So let the current be I2. If you observe the diagram, the current is mentioned as I2 in the catcher cavity. We have actually passed the buncher cavity space, we have passed the drift space, and now it is entering your catcher cavity. So the fundamental component of beam current at catcher cavity. Because when the electrons are nothing but it is flow of charges, which is current. So we are finding out the fundamental component of beam current at the catcher cavity. So we are going to write the current as I2, and it is a function of, it is 2 I0 into J of x. Where this term J of x here is a Bessel's function which plays an important role to find the values for any sinusoidal inputs. Right? So it is a function of the Bessel's function. And the Bessel's function for two cavity Kylstron, the value is defined as 0.582 when the bunching parameter x takes up a value of 1.841. These are actually predefined values or standard values that we will be using. Now from equation number 14, we can actually write delta L, right? Maybe we will try to equate, I'll simplify and then write. So from equation 14, we have already written that x is equal to beta I V1 divided by 2 V0 into theta naught. And we already found what is theta naught. Theta naught is given by omega into L divided by 2. So this is beta I V1 by 2 V0. Theta naught is omega. The drift space length, we defined it as del L if you see in the previous equations, divided by the velocity V0. So from this, the drift space length, the optimum drift space length del L can be found out as, just rearrange the equations. I am taking this 2 to this side. So it is 2 V0 V0 into x divided by beta I V1 into omega. Now we already know the values of x. We know what is g of x values. So this is 2 into x value is 1.841 into v naught into v naught divided by omega beta I v1. So therefore, from all these equations, from this simplification, we find out the optimum length of the drift space. So L optimum, that is del L, it is given by 2 into 1.841 is 3.682 V naught into V naught divided by omega beta I v1. So this is the optimum length of the drift space that we have to decide. Next part, we need to find out the output power of the two cavity klystron. So let us start finding the output power. So we know that a current is flowing, and at the output let us assume a resistor to be present through which the current is flowing. So this current I2 will be a function of the coupling coefficient. So we mention it as output coupling coefficient. Previously it was for the input side, so we mentioned it as V naught Vi. Now it is at the catcher cavity, which is the output, so we mention it as V naught into I2. And let this resistance be RSH, and let the measured output voltage be V2. So we can write the power output as, it is I square RMS. It is I square into R. Power is I square R. So it is I square RMS divided by RSH. The RMS value of current is given by I by root 2 the whole square into RSH. And we know that current is a function of the beam of the electron that is formed. So it is given as beta naught into I2. It is not a single electron component. It is a beam of electrons or the bunch of electrons. So it is beta naught into I2 divided by root 2 the whole square into RSH. So it is beta naught I2 the whole square, root 2 square becomes 2 into RSH. This is your power output. Now we will find out what is I2 and substitute here. So we know by Ohm's law that V is equal to I into R. So V2 will be I is given as beta naught I2. This is the total value of current into R is RSH. So therefore from this I2 is equal to V2 divided by beta naught into RSH. So I'm going to substitute this I2 value in this equation. So V out is equal to, it is beta naught square by 2. I'm going to write I2 square as, this term I'm going to write I2 square as I2 into I2. So I'll have one I2 as such. The second I2 I'll substitute as V2 by beta naught into RSH into, we have one more RSH term. So this RSH gets cancelled, beta naught gets cancelled. So therefore the power output is given by beta naught I2 V2 whole divided by 2. This is the value of output power of the two cavity Kylstron amplifier. Next is we need to find the efficiency. So efficiency, we know it is the ratio of the output power to input power. So efficiency eta is equal to P out divided by P in. So power and output. What is power and output? It is this equation. So it is beta naught I2 V2. So it is beta naught I2 V2 divided by 2. Input power is V into Y. So it's input voltage into input current. So therefore efficiency is given by beta naught I2 V2 divided by 2 V naught into I naught. This is the formula for efficiency of your two cavity Kylstron. Last parameter is the voltage gain, and it is a ratio of output voltage to input voltage. So output voltage, we know V is equal to I into R. So the output current was beta naught I2. The output resistance was RSH, and V1 can be found from equation 14. Equation 14 was the equation for the bunching parameter. So from that we can actually find what is V1. If you interchange the terms from that X equation, we can actually find what is the value for V1. So we had actually found out X as beta I V1 divided by 2 V naught into theta naught. So if you interchange the terms, we can get what is V1. So V1 can be written as, it is 2 V naught into X divided by, it is output. So it is beta naught, not beta I. So it is beta naught into theta naught. So cancelling out the like terms. So this can be written as beta naught into I2 into RSH divided by 2 V naught X divided by V naught theta naught. Now this output value of current I2 can be written as 2 I naught into J of X, because as I told you earlier, it is a function of the Bessel's function, the current. It is bunching of electrons and it follows a sinusoidal distribution. So we define the current in terms of the Bessel's function. So we can substitute in place of I2. So therefore AV becomes beta naught into 2 I naught J of X RSH divided by 2 V naught X divided by beta naught theta naught. So this 2 can get cancelled, and therefore the final equation for the current gain is given by beta naught square theta naught J of X RSH. This I by V is nothing but R. We know that V is equal to IR, or I by V can be written as 1 by R. So this becomes 1 by R. So it is 1 by R naught into the bunching parameter X. So this is the equation for the voltage gain. And to finally state the characteristics of the two cavity klystron, the efficiency is about 40%. The output power, we can obtain average output power of 500 kilowatts and pulsed power of 30 megawatt at 10 gigahertz. And the power gain that we obtain for a two cavity klystron is about 30 dB. So this is about the two cavity klystron and finding out its efficiency, and finally the basic characteristics of the two cavity klystron.